Good morning. Let's begin. The plan for today's lecture is to introduce some applications of multirate signal processing. Having understood and studied the tools over the last 38 lectures, the last two lectures, today's and tomorrow's lectures, will be focused on how do we use these tools and some of the novel ways in which we can think about it. So just to quickly summarize what we have completed as far as lecture 38 is concerned. We wanted to transmit a wideband signal through a frequency selective fading channel. That was the context, and the way we said was that we would introduce redundancy at the transmitter, remove the redundancy at the receiver. Two types of redundancies that we could introduce: zero padding or cyclic prefix. Once we introduced the cyclic prefix, the input output relationship got related by means of a square matrix, which is a circulant matrix, and we used the properties of a circulant matrix in terms of its diagonalizability, using the DFT and the IDFT matrices, with the diagonal elements being the DFT coefficients of the channel response. So basically what we could do at the receiver, at the transmitter, is to produce a signal for which you have taken the IDFT. So when you pass that through the channel, then what we get is a very elegant, very simple structure, which is given by it looks like a set of parallel channels, though they were actually interleaved, they were transmitted through ISI channel. What it looks like is a very clean parallel channel with different SNRs which are controlled by the coefficients themselves, and this is actually doubly advantageous because you can also do water filling based on these channel coefficients. And then when you look at the other end, if you want to bring all of the signals together, then we can look at them as a scaling which will give you the resultant received signal. Equivalently, we can also think of it as parallel channels, all with equal gain but with different noise terms. Different noise variances means different SNR. So again, you can think of it as scaling of the signal with all of them having the same noise variance, or same signal power with the noise variances being modified. Okay, so this was the beauty of OFDM, and it has become one of the most widely used transmission techniques, and I believe it will be used as we move forward as well. So today we move into the applications part. Where are the areas where multirate signal processing is being used, and what are the ways in which we can leverage it? So the first application that I would like to take up, and first of two applications, is in the context of signal quantization. As you know, in our practical implementations of any communication system, we would have to restrict the signal to a finite number of bits in terms of its representation. So anytime we have such a situation where we have a finite number of bits for representation, we have the quantization of a signal. So x hat of n being the quantized signal to which you pass a unquantized signal x of n. Q represents the quantization operation. Okay, and the number of bits of operation, the scaling of the signals, all of these are incorporated into the quantization process. Again, the notion that we have from our basic understanding is that the signal spectrum, if I were to look at the sampled signal spectrum, so the sampled signal spectrum at this point we are able to draw as minus pi to pi. This is the sample signal spectrum, assuming I have sampled it at Nyquist rate. This is the next copy, and so on. So this is 2 pi, right? Pi, yes, this is 2 pi. Okay, so this is the spectrum when there is no quantization noise. Then we pose the question, how does quantization noise enter, and where do I have to keep track of it? We say that, okay, quantization noise is something that we cannot avoid when we quantize. We go through, I am sure you have gone through the analysis of quantization noise. We say that the quantization noise has certain statistical properties. Okay, and we will go through them, but by and large the spectral properties of quantization noise, it is very random in nature, it is uncorrelated, so therefore it is spectrally white. So, we think of quantization noise as something that goes from minus pi to pi, some wiggles, basically it is something that has a flat spectrum, almost flat spectrum. Okay. Now, depending upon how many bits of precision we have used, we will have more or less quantization noise, and if you have used less bits of precision, then what we would end up with is increased quantization noise. Okay. It is still flat, but it is increased in. Now, this is the problem that we encounter with quantization, and it is always a worry for us, is that have I quantized the signal too much that I am not able to recover the or get enough of the information. So, here is the visualization of the process. I have a continuous time signal. I do not know whether we call it XA of t or XC of t, continuous time signal. The process that we have been studying so far is an ideal conversion from continuous time to discrete time. We pass it through a C to D converter with a specified sampling period Ts. This gives us the discrete time representation x of n with infinite precision. Then comes the quantization block, where we have to impose the condition for storage of a transmission. We have to quantize, and the quantized signal is now what we have to deal with, which is x hat of n. Okay. And of course, the quantized signal is what we would encode into a form. It could be 2's complement or 1's complement, whatever form you want to encode. So, maybe you can think of another block either which is included with the quantizer or with the encoding operation. Okay. So, basically we have obtained a b bit representation, which is a quantized version of the original signal. Okay. So, this is the framework. Now, we go back, and now the question that being posed is, does multirate signal processing even help, and if so, how, and how do we leverage it, and so that is the context of today's discussion. Okay. So, the first thing is that we must all be comfortable with what is the normal or conventional quantization. I was checking with the faculty who teach DSP. They said sometimes it is taught, sometimes it may be assumed that it is taught in communication. Communications people say that, okay, we think it is assumed it is taught in DSP. So, in case it has not been taught, this is the part that we are focusing on. So, basically we would like to look at a uniform quantizer. This is the most common one, uniform quantizer with rounding. Okay. We will assume that we have a fairly large number of bits of representation. What is large? 10, 12, 16 bits of representation. So, which means that you have sufficient number of levels to represent the signal. So, very quickly, what does the uniform quantizer do? It for every input signal, it produces a corresponding output signal, which is a finite number of bits of representation. So, the levels, if you were to look at it, are marked off by some uniform step sizes. Okay, we will call it as delta, and you mark it uniformly on the x and the y axis. So, basically this is, and we say that anything between delta, so this is delta, 2 delta, 3 delta, minus delta. Okay. So, anything which is in this anything which is in this range, we will denote between minus delta by 2 and delta by 2, we will denote as 0. Anything between delta by 2 to 1.5 delta is denoted by the next quantization level. Okay. So, then we go up to the next quantization level and so on. Okay. Similarly, we have the negative side as well, and once you have drawn sufficient number of levels, you can you can leave it. So basically this is the quantization, uniform quantization that is happening. All the bins are equal value and then you have quantized it to some levels. So this is a signal where there are positive and negative signals permitted. We would like to have a representation in terms of the number of bits. So the standard convention that we use is we assume that we have a b plus 1 bit representation, and I will clarify that in a minute why we want to do that. So b plus 1 bit binary representation, the plus 1 denotes the sign. Okay, so it's actually a b bit quantization in each for positive values and for the negative values. So binary representation, and again I am assuming that this is familiar to you. I am just sort of giving you the key elements. So 1 bit for the sign and the b bits for the amplitude representation. Okay, so that is what we have done, and typically we would like to represent these values in a range from -1 to 1. Basically we assume that the signal is scaled by its maximum amplitude, and so if you were to think of the bits of representation, so it would be treated as B0 dot, that means that is the one that denotes the sign. Then we have B1, B2 all the way to BB, uppercase B. Okay. So it will be minus B0 times 2 to the power 0, that is 1, plus B1 times 2 to the power of -1 plus B2 times 2 to the power of -2. This is 2's complement representation. The final value is B subscript B 2 to the power of -B. This is 2's complement, and you would have studied other forms of representation. All are fine. Since this is more of an analysis of the quantization error, we do not really spend too much time on this element. Okay, so 2's complement representation, uniform levels from a range of values. Okay, so typically what you will find is that if we have one level denoted as 0, then this could be a typical representation. So if I have a 3 bit representation, so basically we are looking at a 3 bit representation. So one of them will be the signal, the polarity of the signal, the second one, the remaining 2 bits are the levels. So this is how we could have a representation: 0 0 0 representing the 0 value, zeros representing the positive values. So I have level 0 1, 1 0 and 1 1. So if I were to do it on a scale on a +1 to -1 scale, this could be given the level 1 by 4, this would be 1 by 2, this would be 3 by 4, and then go to the negative side. The first value in 2's complement would be 1 1 1, that would be -1 by 4, 1 1 0 -1 by 2, 1 0 1 is -3 by 4, and 1 0 0 is -1. So typically this is how you would see the quantization, and notice that there is, in terms of the negative values, there is one extra value. Okay, you go slightly more on the negative side than on the positive side. Again, if you have enough number of levels, this is not an issue. So again, it is a point to note that invariably the quantization will have one extra level on the negative side than on the positive side when we do the 2's complement representation. Okay, so what is the step size? The step size that we have worked with, that is the delta. Step size delta, there are 2 to the power of b plus 1 bits, right, that those are the number of levels that we can get, and I go from a positive maximum value to a negative maximum value. So if xm is the extreme range of my signal, so if my signal lies in this range xm to -xm, and I want to quantize this into the number of bins that are available to me. So this would become 2 times xm, that is the range that I have to quantize, and I have 2 to the power b plus 1. So this is this delta is often related to or denoted as of m divided by 2 to the power of b. And so this is a but you know where it comes from because of the b plus 1 bit representation. So the quantized signal x hat of n, which has been quantized with a b plus 1 bit representation, can be actually recovered or it can be related to the maximum value xm, right, that is the peak value, and the quantized signal has been represented in the range once you have scaled your signal by xm, then you can quantize it in the range minus 1 to plus 1, that is xb hat of n. Okay. Or if you want to think of it as a scaled signal, take x of m to the other side. So, you take your discrete time signal, scale it by the maximum magnitude and then quantize it, because now it is in the range plus 1 to minus 1, that is xb hat of n. Okay. So, I think the quantization framework is clear. It is a uniform quantizer, it is a rounding quantizer. So, basically once you go past the half level, you are going to be quantized to the upper level, that is where the rounding element comes. So, here is a general statement that the errors that you will see in your quantized signal, if you were to write your quantized signal as the unquantized signal x of n plus e of n, some error sequence, which is, we can say that typically e of n has a range of values. It goes from minus delta by 2 to less than delta by 2, provided you have not reached the sort of the upper level, the extreme levels. If you have reached, if you have crossed that, then it is clipping, but in the range of the quantizer, this is typically satisfied. So, this is a good way to look at the signal. Okay. So, some statistical assumptions about E of n, which helps us in the quantization or in the analysis of the quantization, is that E of n is a uncorrelated sequence. It is basically from sample to sample, it is uncorrelated, and it is a very reasonable assumption, because if you were to look at a signal that is varying like this, at a given point in time, this is the sample value, the quantized level could be here. Okay. The next instant of time, the sample value that could actually be on a quantized level itself. The next instant of time, it could be sampled here, but it could be quantized to a higher level. So, basically you can see that from sample to sample, there is no necessity or there is no underlying correlation. So, we make the following statements and assumptions, that first of all, that the error sequence E of n may be positive, negative, 0, and it is uncorrelated to the signal, is uncorrelated with the signal. It's a very helpful assumption. It's uncorrelated to the signal. Okay, that's the first signal x of n. The second element, E of n is a white noise process. White noise process, that means it is uncorrelated from sample to sample. Okay. And you can also think of this as a sample of a Whitson stationary process. That means whatever things like mean, variance and other parameters are not dependent on time, they are constant. So, that is another aspect. So, E of n, we consider it as a sample sequence from a Whitson stationary random process, a sample sequence from a Whitson stationary random process, RP random process. Okay. And the last assumption, that the quantized value of E of n is uniform, that the probability is uniform. The PDF of E of n is uniform. Okay. These are the assumptions. So, in other words, the PDF being uniform says that the error goes from minus delta by 2 to delta by 2. The probability is that all of these values are equally probable. So, I have a height of 1 over delta, that is my PDF, probability distribution function of the error signal. So, this is the probability of E of n of E. Okay. So, basically this is the framework, this is what you would have used to analyze. So, using this framework, please verify that these are the results that you would have shown or derived. The mean value is 0, uniform, both positive and negative values, straightforward to show. Second one is the variance of the error. Okay. This one says I go from minus delta by 2 to delta by 2. The variance means I have to do E squared, PDF is 1 over delta times dE. This comes out to be delta squared by 12. Okay. So, this is also a result that is well known. Delta itself we have said can be written as x of m divided by 2 to the power b, or you can write it as 2 power minus b times x of m. So, so this can actually be written as 2 power minus 2b x of m squared divided by 12. Okay. So, here comes the first major equation or the outcome of this analysis, which is a very useful tool for both communications and signal processing engineers. Signal to quantization noise ratio. This is not channel noise, this is quantization noise. Okay. So, on top of it the channel may add, but right now at the very representation stage itself there is some noise being introduced. So, signal to quantization noise ratio defined very similar to what you would do for the signal to noise ratio. Basically it is 10 log base 10 of the signal power sigma x squared divided by sigma E squared. Okay, sigma x squared representing the signal before it, that is the signal x of n, and sigma E squared. And if you go ahead and substitute for this from the previous expression, this becomes 10 log 10 of 12 times 2 power 2b times sigma x squared divided by xm squared, sigma x squared by xm squared. Okay. So, now what is xm? The maximum value that it can achieve. Sigma x squared is the variance of the or the power of the signal, right, sigma x. So, that is a very important element, just so that you are feeling comfortable with it. For a sinusoid, if the peak of the sinusoid is x of p, what is the RMS value? Sigma x will be 1 by root 2. So, there is a relationship between the extreme value and the RMS value, and that is what we are capturing here. So, now if you were to write down this this equation, this would be 10 times log base 10 2 power 2b plus 10 times log base 10 of 12 minus 20 times log base 10 of xm by sigma x. Okay, I have deliberately inverted the ratio and written it. Okay. So, simplify this equation, what you should get is the following. It should be 6.02 times b plus 10.8, the other term, minus 20 log base 10 of x of m by sigma x. Okay. So, the key question is how are you going to design your quantizer? You have to tell what are the range of your quantizer, and of course, how many bits you are going to do. So, if I choose my range to be xm and I have chosen b plus 1 bits as the representation, this is the equation that tells me what my signal to quantization noise ratio is. Okay. Now, usually for most signals we can sort of specify. Okay, how do I set these up, the limits? So, you can say that for example, you can say that I will choose xm to be equal to 4 times sigma x, basically 4 times sigma on this side, 4 times sigma on that side. So, that is the range that I want to cover. So, if you take some assumption like this, you are bound to capture most of your input signals. Of course, there could be occasionally an input sample that goes outside, but by and large you have captured it. You can do 3 sigma, 5 sigma, whatever it is. Keep in mind that the larger that you want to keep x of m, it is going to reduce your SQNR, right, because that means that with a finite number of bits, that means your quantization error is going to be more because you have a larger range to cover. So, this is a important choice. Now, one of the common choices is 4 sigma. Therefore, if you make that assumption, then we have 20 log of 4, which comes out to be 12.04. So, if you go back and substitute, your SQNR now has the following: 6.02b minus 1.25, this in dB. Okay, so very cleanly you have now linked your SQNR to the following result. Okay, so this is where you get that thumb rule which says 6 dB per bit. Okay. Many times you will see people saying, oh, what is the quantization noise you want? Quantization noise. If you say I want to get 96 dB, they will say 16-bit representation. How did they get it? How did they, without even computing everything? Because they say, okay, if I have 16 bits of representation, the SQNR will be of the order of 16 times 16, 16 times 6, and that is 96 dB. Okay, so this is where that 6 dB per bit rule comes. And so if you want to go from 64 dB SQNR to 96 dB SNR, you know exactly what you have to do in terms of the, so this is the quantization noise and issue. So again, up to now nothing new, nothing different. So the key question is, can multi-rate techniques make any difference? Multi-rate DSP help, or can it do something? And surprising result which says that if I use multi-rate DSP, I can reduce the number of bits of representation and I can still maintain the SQNR. Okay. Now you may say, okay, to what extent can you reduce the number of bits of representation? The answer comes out to be, I can go down to 1 bit representation. So 1 bit representation, if you want to think of it in terms of the conventional approach, if this is your signal spectrum, remember we drew those lines. Okay, this is the quantization noise. If you had 16 bits, it will go up here. 1 bit means you are pretty much swamping your signal with noise. So almost nothing you can do with the, but so with a conventional method, if you go down to 1 bit quantization, nothing can help. But with multi-rate, the claim is that it can go down to 1 bit. So here is the first step. The first step is oversampling. Okay, so let me just give you the flavor of it. Since this is more of an application talk.